we know that we've seen how the electric field can be obtained by a scalar potential phi, and the magnetic field can be obtained by a vector potential A. And we might want to see what that looks like in terms of tensors. So these two objects will appear in a tensor. So let's maybe remind ourselves that B is obtained as the curl of the vector potential, and the curl of E is minus dB by dt, right? Faraday's law, and therefore we're taking the curl of the electric field, which let's do, well, curl of electric field equals, so minus, so in other words, I'm trying to build the electric field in terms of phi, and we normally remember in the static case that E is equal to minus the gradient of phi, but actually that can't be enough, because we can see here that curl of E, if E is the gradient minus the gradient of phi, then it becomes minus the curl of the gradient of phi, and the curl of the gradient is identically 0, so that's going to vanish, and that won't be enough, so we need some other term here, plus some, well, we can see what it has to be, because we need B is equal to the curl of A, so this has to be, this ends up being the curl of, and we have a time derivative here, so we're going to end up having to include a term like that, which of course gives us minus, we can pull the time derivative out, d by dt of the curl of A, and we see that it's minus dV by dt, and so the electric field actually is minus gradient of phi minus dA by dt, and we can construct a tensor FAB that has these objects, that comes from these objects. So really a 4-vector has this as the 0th component and these 3 components as the spatial components. And so we want lowered components because we want to take derivatives. We see that these things are related to derivatives of the potentials to get the fields. So we want a derivative in x, let's see, FAB equals derivative of AB with respect to XA minus derivative of AA with respect to XB. And we want to see that we recover these equations here in tensor form. So we get to choose our indices, between 0 and 4. So let's look at F. Let's look at F 0, 1. So that's dA1 with respect to x0. That's the time derivative minus dA0 with respect to x1. Let's continue to look at these terms with zeros. We know these are lowered electric field components. dA2 in x0 minus dA0 in x2. And F03 is dA3 with respect to x0 or time minus dA0 with respect to x3. And we can see that these are the components of the electric, these are electric field components. It's not surprising that it's going to be this, but we can see that we're getting minus dA by dt minus the gradient of phi here. And the indices without 0 here, right? We have combinations of, we could do 1, they're anti-symmetric, of course, as we know, but we can do 1, 2, 1, 3, and 2, 3, and in this case we have 1, 2, which is dA2 with respect to x1 minus dA1 x2, and then we can do F1, 3. It's dA3 x1 minus dA1 and x3, and F2, 3, which is 3, 2 minus A2, 3, and we can see that these are magnetic field components. So this is B. These are the 3 components of B equals curl of the vector potential.